Prof, you belum turn off your virtual.
Oh ya, patutlah. Saya pelik. Saya pula pelik. Nanti macam mana nak ada virtual background kat kelas? Macam-macam lepas 2 tahun ni. Alright. Tulis kat virtual background 3.7 is coordinate vector and change of basis. Yusof kan nama dia? Yusof kan? Yusof ada tak? Tengok.
Yes, doctor. I'm here.
Dah ambil buku ke belum?
Lepas ni.
Lepas ni tu apa? Lepas kelas?
Yes, after this class.
Okay, kalau tak ada, jaga. Lepas kelas pukul 1, pejabat tutup Kena ambil during office hours.
Okay, doctor.
Okay, so coordinate vector and change of basis. You know, if you have a basis for a vector space V, okay, so vector space V can be any of those vector space. All right, Rn, Pn, matrix n by n, but normally we don't talk about the continuous function because cannot find a basis for all, so the 3-1. So we have this vector space V, we have a set S, and then we have a finite vectors. It's always this, okay, V maybe the dimension is n, right? This is finite, m of them. Okay, I don't put this n because some of them is n, right? Like P, like R, Rn has to be n, but Pn has to be n plus 1. So I just put m. Okay, now if there is a V, small v, or last time I call it y, if there is a v or a y in V, it can be in S or outside S. Then you have for all y in V, there exists C1, C2, Cm in R such that y can be written as this, right? If this S is a basis, okay? If S is a basis, S spans V. And what does it mean? S spans V means for all y, any y in V, there is this C1 until Cm in R, such that this y can be written as a linear combination. Theorem 3.9 said not only there exists, but not only it exists, but they exist. Bukanlah, it's not tanda seruan. It's unique, Jerit lah. That is the symbol for unique. Okay. Not only they exist, but it's unique. Tak akan dapat banyak jawapan. So, because when we solve the equation, then we get a unique answer. Okay, so then we can do coordinate vector. This is the basis. Okay. Now, I will write the definition. Let S equal U1, U2 until UN be a basis of a vector space V. And V in V. the coordinates of V relative to the basis S, the coordinates of V relative to a basis S is a scalar C1, C2, Cn in R such that V is C1 U1 plus C2 U2 plus Cn Un. This is called the coordinates. The coordinates of V relative to the basis S. If I change the S, the coordinate will change. What is it? It's a scalar. It's a real number in which we take all these coefficients. We put them together. The coordinate vector of V, the coordinate vector of V relative to the basis S is denoted by we write the bracket V sub S, C1, C2 until Cn. N. So it's nothing new, right? You just write and find the C like before, and then you pick all the C and you write as a vector. Okay, it's actually the solution, right? When we do all the matrices, row operation, just take the final answer, put in a vector, it becomes the coordinate vector. Sometimes we call this a component of V. Sometimes, but not always. Some books, they call it this component of V. Okay. Now, at the end of the previous section, I did not mention about standard basis. Okay, if you have read the whole thing, you might have realized I put in the notes about standard basis. Where is it? I mentioned about the dimension. Okay, example 316 under section 3.6 basis and dimension. There is the example. Okay. So under this one. I cannot find 3.6. Oh, dia berubah section number. I see. Bukan 3.6 ada dekat dalam ni. In the notes is 3.6. It's okay. I will write out the standard basis, yeah. Normally, the question won't give you standard basis because it will be too easy. Okay. Lama. Sekejap. Dia bunyi-bunyi pula. Notification setting. Notification. Okay. Okay. Okay, for R, we normally start with R2 because R is just 1. So this. Okay. If you draw this, you will get this and this. This is very easy to show that it's a standard basis. It's a basis. It spans any xy can be written as x times 1, 0 plus y times 0, 1, right? So there exists C1 and C2. And if you let this equal to 0, you will get C1 is 0, C2 is 0. So it's linearly independent, right? Or the determinant of A is not 0, it is equal to 1. So this is called a standard basis. Any xy can be written as a linear combination of these two. Just multiply this by x, just multiply this by y. Yeah. So if you have S equal this is not R2 apa ni H apa tulis ni S is 1001 is a subset of R2. S is a basis of R2. So if I give you V equals like 2, 3. Yeah, if V is 2, 3, it's easy to write this as 2 times 1, 0 plus 3 times 0, 1. Exactly that, right? Because it's just straightforward. So VS is 2, 3. The coordinate vector. So that's why I said we normally won't give you the standard basis in the question. We'll give you something else. For example, S prime 1, 1 plus say 0, 1. Comma. This is also a basis. So a basis is not unique. Okay, there are infinitely many bases for one vector space. I can give you infinitely many questions. As long as these two vectors, it has to be 2, yeah? As long as these two vectors is not a multiple of each other, then it is a basis of R2. Okay, I repeat, they have to have 2 vectors and they are not multiple of each other. Or when you put as column, the determinant is not 0. Okay? Okay. And there is no 0 vector. Multiple 0 vector is a multiple, right? 0 times any vector. Okay. You can show it's a basis by finding C1, C2, right? And solve. What is the vector, coordinate vector? I have to give you a vector. To show it's a basis, you put xy, then you solve. Then you put equal to 0, 0, and then you show C1, C2 is 0. But to find coordinate vector, I have to give you a vector. So, for example, V is 2, 3. Find C1, C2 in R such that C1, 1, 1 plus C2, 0, 1 equals 2, 3. It is not a requirement that you have to use the 4 methods in chapter 2. You can use your school method as long as we got C1 and C2. Yeah? So if you write out, you will get C1 equals 2. Terus kan? C1 equals 2. C1 plus C2 equals 3. So C2 equals 1. And you can check. If you put 2 here and you put 1 here, you get right. Okay. So Vs equal C1, C2. 2, 1. If it's quite complicated or it's like R3, you might want to do Gauss or Gauss-Jordan. Okay. To find what is C1, C2, C3. Okay. Okay. The example in your notes give you a different V, is okay, you can go through. Okay. And then the next example, different basis, very similar to this. All right. Another question is a little bit different. If you are given this, how do you find the V back, right? Okay. So you are given, oh, I haven't finished with the standard basis. For standard basis for R3, oh, no wonder I put R3 there. Okay, for R3, I want to put R3. S is that is the standard basis for R3. And then R4, so you see there will be 4, and then the 1 will be at the first place, second place, third place, fourth place. That is R4. Okay, dot, 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 Rn. How do you write the standard basis for Rn? For Rn. So S will be 1, 0, 0, dot, dot, dot. 0, 1, 0, dot, dot, dot. Dot, dot, dot. 0, 0, dot, dot, dot. 1, 0, plus 0, 0, dot, 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 0, 1. You see the pattern, right? There are n of them. There are n component. The one, then you go to second, you go to third, dot, 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 second, last, last. Yeah, this is the standard basis for Rn. And then for Pn, before Pn, P1, P2, Pn. The dimension is n plus 1. So P1 will be 1 x. 1 and x, or t, yeah? P2, 1 x, x squared. 3 of them. So the dimension has to be n plus 1. Dot, 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 1 x, x squared, x n minus 1, x n. So this you have to know, the standard basis. Okay. So the question in this section can choose any of these 3 vectors. Maybe you will be given P2, maybe you will be given matrix. Okay, this one is okay? Okay. Matrix for, I do like this, bukan equal lah ya, vector space. So S is, you need to have 4 because it's n times n. 2 times 2 is 4. 1 here, 1 here, 1 here, 1 here. Because I put accordingly to the row. This is the standard basis of 2 by 2. So if it's like 3 by 2 or 2 by 1, then you just put the 1 accordingly. Okay? All right. I finish with the standard basis, I want to show another type of question regarding coordinate vector. This in the notes. Let S be 1, 0, 0, 1, 1, 1, 0, 1, 1. Okay, so this is a basis of R3. Maybe you will be given this, and then the first question, show this is a basis, right? Show this is a basis. So it has to span, and it has to be linearly independent. And go back to the example I gave you 2 days ago. Find C1, C2, C3. So C1 times this, plus C2 times this, plus C3 times this is X, Y, Z. Then put as column. You can either show the answer is consistent, C exists, or the determinant is not 0, C exists, so it's span. And then for linearly independent, the n you put 0, 0, 0, still the homogeneous system is has unique solution, C1, C2, C3 equals 0. So it's linearly independent, so it is a basis. Yeah, exactly like we did. Now with this question, given Vs is 351, -1, find V. Okay, if you remember, when we put Vs is C1, C2, C3, this is given by this. This is how we get this, right? You have this linear combination, you pick C1, C2, C3, multiply by this equal to this V. Okay, so in this case, you already given this, so you put 3, 1, 0, 0, plus 5, 1, 1, 1, minus 1, 0, 1, 1 is V. Right? Then just calculate. This is equal to 3 plus 5 is 8 minus 0. 8. 0 plus 5 is 5 minus 1 is 4. Ini apa ni? 0 plus 5 is 5 minus 1 is 4. So this is easier, right? You just get directly this. Okay. One more question is we change the S. 1 minus x plus 3x squared, x squared, -1 plus 2x plus x squared. 1 minus x plus 3x squared, x squared, 1 minus 2x plus x squared. This is in P2. Actually, this is very similar to R3. Okay, the dimension is n plus 1, in which this is like 1, -1, 3, right? 1, -1, 3, 0, 0, 1, -1, 2, 1, right? When you write as a matrix, it will be like 1, -1, 3, 0, 0, 1, -1, 2, 1. So the process of showing is a basis, putting in ABC, and solving, very similar to R3. Don't get confused with the polynomial. And the question is, given Vs is 2, -1, 1. Okay, 2, -1, 1. It's very similar, just that your answer has to be V, which is in P2, so it's a polynomial. Yeah, but the working is the same. So you just put 2 times this minus 1 times this plus 1 times this. Then you get your answer because you already given the coordinate vector. 2 times this, negative 1 times this, plus 1 times this. Okay, so 2, nothing, right? Two minus 1 is 1. Negative 2x minus 2x. 6x squared minus x squared is 5x squared, 4x squared. And this is in P2. So that's the answer. Right? Okay. The same thing for matrix. Nur Suziana, you have a question? Plus 2x plus x squared. Two minus 2x plus 6x squared minus x squared minus 1 plus 2x plus x squared. Okay. Right. So 2 minus 1 is 1. Negative 2x plus 2x habis. 6x squared minus x, 5x squared plus 1 plus 6x squared. Okay. Siapa tadi? Suziana. Okay. Alright. Third one. Third example. Third example. S is 1, 0, 0, negative 1, 0, 0, 1, 1. Okay. And this is 3, 5. So this is in matrix 2 by 2. Okay. This is not a basis actually. I cannot put that this is an ordered basis. This is not a basis. This is just a set. Okay. You change a little bit, the question. Oh, how come it be like this too? I add 2 more, yeah? How do I know which one to add? I have to make sure it's not a linear combination or multiple. Yeah, that's how I add these two. So now we have enough 4. If you want to double check, if I write like this, then you take to find the determinant. You take this one, right? Then you take this one. So you take this one. Then you get 1. So the determinant is actually 1. okay, by choosing the row or column. So I know this is a basis by determinant, not 0. Okay, so this cannot be just 2, right? I have to give 4. Suppose I give like this. Well, actually, the one that I give you is not a basis of the whole matrix, but it's a basis of its span. Okay, it span just 2. If it's in R4, if you have 2 vectors, it will span just a plane. But it does span something. It span a plane, but not the whole 4 dimension. Yeah. Okay, so by this one, you just multiply. It's very easy, right? Then you get the answer. Yeah. Okay, 1, 0, 0, 3, 0, 2, 4, negative 1 plus 2 is 1. Then you get the answer. Okay. Straightforward, yeah? Okay, the next one that I have to show is transition matrix. We have this set S. You have probably another one. Because I mentioned for a vector space, it can have infinitely many bases, which is different, as long as it is finite, right? We have seen, for example, for R2, the standard basis is 1, 0, 0, 1. It can be 1, 1, 1, 2, 1, 2, 2, 3, as long as its determinant is not 0 or it's not a multiple, right? So I can give you many bases. For example, for dimension n, I can give you this basis. Okay, the question is, we want to change a basis. We want to change a basis from S to S prime. How do we change this? For S, we have for V in V, we have the coordinate vector of V related to S. For S prime, we also have coordinate vector of V related to S prime with the same V. Yeah. Now, the formula is Vs prime is P Vs. This is the formula. And P is the transition matrix from S to S prime. Okay, how do we get P? How do we get P? The computation is very familiar to you for now, but how do you put it in terms of matrix? Okay. So let's see. I write everything in words, yeah? So let S and S prime be two bases of a vector space V. Then the transition matrix from S to S prime is a matrix P where the columns of P are the coordinate vectors of S which are the coordinate vectors of S relative to S prime. So you have to calculate how many n many times. The coordinate vector, the column of P. So wait, before this, let me write again. Let S be U1, U2, UN, S prime be U1 prime, U2 prime, UN prime. So P is coordinate vector of S relative to S prime. So it's U1, S prime. Second column, U2, S prime. Until last column, UN, S prime. So just now we have only one V, right? The third examples that I have before, only one V, you calculate. Now we have three. If there are three times you have to calculate over and over again. Okay, let's see. Okay, look at the proof, yeah? The proof is how you got this in terms of this formula. You get Vs prime is P Vs. The theorem and the proof is your responsibility. Okay, now let's look at one example. This is in the notes, so you just understand when I explain. You are given S equal, I just put in the question, yeah? U1, U2 is the easy one. The standard basis. S prime is 1, 1, 2, 1. Okay. A. Find the transition matrix from S to S. Okay. So according to this, you have to find the coordinate vector of U1, which is in S with respect to S1. So this means U1 is in S. Okay. Then you have to put this is C1 with respect to S prime. And this we call it U1, U2, U1 prime, U2 prime. So this is C1, sorry, U1 prime plus C2, U2 prime. Okay. All right. So you have to put this. Let me rewrite. U1 S prime is C1, C2. So you put U1 is equal C1, U1 prime plus C2, U2 prime. That is how you get this coordinate vector U1 coordinate with S prime. Okay, let me repeat. This is C1, C2 such that you have this equation. So how to find this is by writing this out. So your first vector is 1, 0, 1, 1 plus 2, 1. Okay, this C1, C, where is the C2? C2. This C1, C2 will be your coordinate vector for the first one. Once you get the answer, all right? Then you go with the other one, 0, 1. Calculate again. So C1 with the same 1, 1 and 2, 1. And for solving C1 and C2, you can use any method as long as you get the answer. But I will use the Gauss-Jordan elimination method. So you will write 1, 1, 2, 1, 1, 0. Okay. The other one is actually the same matrix, right? You put 1, 1, 2, 1, 0, 1. Okay. So you can solve this easily and you will get the answer C1, C2. But if you realize you will be doing this 2 times, why don't I combine 1, 1, 2, 1, 1, 0, and 0, 1. Okay, I explained this actually in the notes. So let's see. Okay, so this is negative R1 plus R2. And this gives 1, 2, 1, 0. I put this dot, dot, dot because there are 2 vectors at the end. They are not a matrix. 1 for the first one, 1 for the second one. So negative R1 plus R2, 0, negative 1, negative 1, 1. Please correct me if I did something wrong here. Yeah? So negative 1 and add. And negative R2. So this one will give 0, 1, 1, negative 1. Multiply this by negative 1, 1, negative 1. Still copy. And the last one will be negative 2, R2 plus R1. And this will give you the answer. Okay, which is 0, 1, 1, negative 1, 1, 0. So negative 2 plus negative 2 plus negative 2, which is 2, and then plus. So this actually is your first one. In P, this is your second column in P. So your P is actually negative 1, 2, 1, negative 1. Okay, so this is transition matrix from S to S prime. I combine so I don't have to do double work, right? Because the computation is similar. When you do this, you see they are the same S. So this is the transition matrix from S to S prime. If they ask from S prime to S, you have to put, so the transition matrix here, from S to S prime, you put S prime first and S on the right. If the question find the transition matrix from S prime to S, from S prime to S, you switch. You put S first to S prime. Don't get confused. Then you get totally the wrong answer. Okay, so I repeat, if you want to find P from S to S prime, the transition matrix, you put S prime first, S over there. Okay, the computation is just the normal computation. We put the first S prime vector here, the second one here, and you put the other vectors inside. Imagine if I ask you the question from S prime to S, I won't ask you that question because it's very easy. If I ask you what is the transition matrix from S prime to S, you will put S first, right? You will put and the answer is already this, because this is already row reduced echelon form. No work needs to be done. So the transition matrix is just 1, 2, 1, 1. Write your answer in terms of matrix. Okay. Any question? That's for the transition matrix. Oh, there is a part B. There's a part B. Let me finish this, then we take a break, yeah? Okay, part B says, use formula Vs prime is PVS to find Vs prime if V is 7. All right. Before we use the formula, suppose we don't have the formula. Okay, suppose we don't have the formula. Suppose you want to find this if V is this. Go back to my example before, right? You will write V S prime is C1, C2. V S prime, yeah? V is C1, 1, 1 plus C2, 2, 1. And this is given 7, 2. We want to find C1, C2. Okay. Then you will do again 1, 1, 2, 1, 7, 2. Again, like just now. 0, -1, -5. Zero, 1, 5, 0, 1, 5, 1, 0, -3. So you get the answer. You get the answer. This is equal to -3, 5. Check. I'm checking, yeah? Yes. This is the old method, the definition method. Okay. Now they want us to use this to find this. So using formula Vs prime equal P times, oh, what is Vs? Okay, standard basis. Okay, so VS for the standard basis is just V. Remember I said just now, if you have like 1, 0, 0, 1, you want to find the vector for 2, 3, it's 2 times this plus 3 times this, right? So it is the same 2, 3. So for standard basis, the vector, coordinate vector for the standard basis is the same thing as V. That's why the question is like this, because VS, standard basis, the coordinate vector is just V, which is 7. And the answer is 7, 3, 7 minus 2, 5. -7. Okay. Where is the answer just now? Ah, see, it's similar. But easier, right? We just multiply. If somebody else asks you another V, if you use the definition, you have to do this again. But if you use the matrix, you just multiply. Because we use the standard basis. Okay, let me explain again about why VS equals V in the standard basis. Okay. Say V is XY, right? You want to find VS, right? This is C1, C2, such that C1, 1, 0 plus C2, 0, 1 equal XY, right? VS is C1, C2, meaning V, which is XY, is C1 times 1, 0 plus C2 times 0, 1. You want to find what is C1 and C2, but because this is so easy, you multiply, you will get C1 is X, C2 is Y. Yeah, that is why, tulis ini je lah, XY, which is actually V, which is actually your V. Then you ask me, why you can write horizontal and then you write vertical? But it's okay. The horizontal you transpose is still vertical. So it's the same number, yeah? That is why if S is a standard basis, the coordinate vector of any V in the vector space associated to this S is just the V. Yeah, that's why we multiply by just the vector, we get directly the answer. If you give me 100 vector, I can find the coordinate vector with this not standard basis, then get the answer. Rather than I try to do this calculation 100 times. Okay, so this is the main thing why we have this transition matrix. Okay, lupa pula. The first question is find the transition matrix from S to S prime. Second one, find the transition matrix from S prime to S. Okay. Number 3, given VS equal 2, 1, negative 2, using the formula VS prime equal PVS, find V. Okay. Now, these two bases, they are not standard bases. Yeah, standard basis would be 1 t squared. That is standard basis for px, 1x x squared. This is not standard basis. All right, so by definition, you need to multiply C1, C2, C3 because any V in P2, if V in V can be written as A plus BT plus CT squared. Any polynomial can be written in that form. If you want to stay with X, Y, Z, it's okay. You can write X plus YT plus CA plus ZT squared as X, Y, Z, real number. But be very careful. If the question change polynomial in terms of X, you cannot use X, right? It will be X times 1, Y times X. Oh, you get confused. All right. Okay, so when you write out the definition, you will write this equal C1 times this, C2, and so on. All right. Okay, so now to find the transition matrix from S to S prime, we will write. This is in the book, so I just erase first. The other way around, we can do two types, right? For this one, we will write S to S prime. We can write S prime S. And S prime is the coordinate of S. And then for the second question, we can do either this or we can do the inverse. Okay, why is it the inverse? Vs prime is P Vs. Okay, now you multiply the left by P inverse, right? This will give Vs is P inverse Vs. So the transition matrix, the other one, if you call it Q, is just the inverse. Suddenly, if you need to prove why the transition matrix is the inverse, this is the answer. You just multiply the left by P inverse. So we'll see if you like this one or you like this one, because this one can use row operation or this one can also use the join method, right? So this go back to chapter 1. Okay, so in that case, I erase, yeah? In that case, you will write S prime 1 t squared. Okay, 1, negative 1, 0, 2, 1, 0, 1, negative 1, negative 1. On the right side, you put 1, 0, 0. 1, 1, 0. 1, 1, 1. So this one go back to chapter 1. Yeah. Okay. So negative row 1 plus row 2. Right? This is already 0. So you get 1, 2, 1. 1, 1, 1. Okay. No. Just add, right? Just add. 0, 3, 0. 1, 2, 2. 0. Oh, I can do this. 1, 0, 0. In my previous examples, normally my answer are all integers, right? And it's not always the case. In this one, I changed the example to not be integer. Yes, okay. Okay, so you want to make this one. Yeah, you want to make this one. Many students, they said, oh, I want to use this 2 to make this one. Boleh tak? Don't go back to the previous row. The first row is already done with. Don't use it to make it S1. Nanti masuk apa? Roundabout tak keluar. Kan? Drive, pusing, memang tak akan keluar if you use this. Because if you take this to make this one negative row 1 plus row 2, the 1 will go here, right? Then this become 1. Tadi penat-penat dah 0 kan? You want to make it again 1. So if you have to use the row below. But there is nothing below, right? It is 0. So the only choice that you have is multiply by 1 over 3. That's the only choice. Okay. Luckily, there are not so many things to do left, right? Because this is already 1. Okay, so I do this 0. So negative 2, row 2 plus row 1. I can, okay, this is already changed. So this, this okay. Negative 2 and add. Negative 2 and add. Negative 4 and add. Negative 4 and add. Oh, this one is negative 1/3, yeah? That's another typo kat situ kan? I have to double check on. Kadang-kadang kiraan dia semua betul tapi typo dia. Betul tak? Is this right? This one is it right? Okay. Yeah. Negative 2 and add. Right. Okay, so P, yeah? P is equal to
Prof, belum habis. Still got one more 1.
mana?
There's still another 1 in the first room.
Oh, no wonder. Tak nampak. Oh yeah, there is this one. negative row 3 plus row 1. Okay. 0, 0, 1. 0, 0, negative 1. 0, 1, 0. 1 third, 2 third, 2 third. 1, 0, 0. Okay, 1 third. Negative 1 third. Negative 1 minus 1 minus 1 third, 2 third. Okay, so it's okay. Okay, so we get the answer. P is copy, yeah? Okay. For the second one, just find the inverse. I think that is easier. Then you have to go through this and switch. And the second one, Q is P inverse. Okay. The third one, just multiply. VS is PVS. 3 VS is PVS. So you have to multiply this P with the question already on give 2, 1, negative. So directly you get the answer for the third one. Yeah. And then they ask you to find the V. So this is VS. So V is negative 1 times U1 plus 0 times U2 plus 2 times U3. So negative 1 times, in the question, yeah, this is S prime, yeah. Okay. In S prime, yeah. So 1 minus T, this is just 0, I don't write. And 1 minus T minus T squared. So negative 1 plus 1 plus T minus 2T minus T minus 2 T squared. You can just leave your answer like this. Okay. So that's it for this section. So the section has the definition and how you can find it for the coordinate vector. Then for the transition matrix, you have again the definition and then the method to go from S to S prime and then go back by the inverse. Okay. All right. Now we open to any question so far, if you have for this chapter, up to now. Siapa yang tanya last class di exercise 4B dah dapat jawapan belum? Or you still want me to explain? Siapa yang tanya hari tu? Belum sempat jawab? Cuba angkat tangan. Raise hand. Okay. Nurin Anisha. Masih tak dapat jawab atau nak saya tunjuk?
Doktor tunjuk.
Okay. Saya padam Okay, after this, if you would like to see some samples, hari tu Dr. No pun ada dah tunjukkan of test 2, I can give you, just mention it in the group. Ataupun letak kat chat nak ke tak nak. Tak nak, saya tak payah bagi. Okay, 4B. Okay, 4. Determine. Kalau ada jawapan belakang salah, bagi tahu saya. Kadang still ada typo juga. Whether W is a vector space or not. Okay. Part A, because there is a number 0, so we know it's a vector space. Okay, it's a subspace of M2 by 2, right? For the second one, A11, A12, A21, A22, A11 plus A12 is 0, Aij in R. You know you can change a question to make it easier. Okay, if you don't change it, then you have to use the condition. If you change it, you will write like this. A11 plus A12 is 0. Okay. Therefore, A11 is A12 is negative A11. Yeah, to make it easier, we can write like this. So this is A11, negative A11, A21, A22. Aij in R. I changed the question like this. Okay, so 0 vector of M, is it in W? Yes, since 0 vector of M2 by 2 is equal to 0, 0, 0, 0. And 0 is real number. A11 is 0 is equal to negative 0 is, which is 0 is A. Oh, sorry. 0 is in R, this one, right? And 0 is negative 0. Because it is, actually, if you don't write, tertinggal lah in W. Since. Macam tu lah. Yes, since. Oh, I have S. So tadi dah betul lah. Tadi dah betul. I have this yes. Okay. 0 is in W. Yes. Since the 0 matrix is 0, 0, 0, 0. And I want to see whether this match. This has to be all real number. Yes. This has to be the negative of this one. Okay. So 0 is negative 0. What if I don't write this? Tolak markah tak? This is really straightforward actually. If you mention something, just put everything, then ada alasan nak tolak markah kan? Just explain your reasoning. U plus V is in W. Okay, what if you don't write this, you use this? How do you do it? Okay, then you will write this and A11 plus A12 is 0 plus 0 equals 0. Yeah, Nurin? If you don't change the question to this, you can still use this. Just add, is it equal to 0? Then it's okay. you write like this. Okay. This one is easy. You just add, right? U is A11, negative A11, A21, A22. Say V is B11, negative B11, B21, B22. So U plus V is A11 plus B11. You can put negative outside, right? In W, this is very important. This is the reasoning. Because I can see already the form. This is negative of this. Okay, this is enough. If you don't use this, you will use this with this condition, another one with that condition. When you add, you try to add this and this using this condition is equal to 0 plus 0 equals 0. You can also use that. The two methods. Yeah, the other method, saya padam eh. So if you use the other method, tak tulis dalam bentuk tu, you will have U is the original one, yeah. This one, you have 1, 1, 1 plus A12 is 0. Then you have this one with B11 plus B12 is 0. Then when you add, you want to check this condition. Okay, so you add A11 plus B11 plus A12 plus B12. Is it 0? Oh, you rearrange. This is A11 plus A12 plus B11 plus B12. But that is equal to 0 plus 0, which is 0. Okay, so then you said this is also in W. Nurin? Hilang. Bukan tanya soalan.
Yes, Doktor. Doktor nak tanya, kalau kita nak tunjuk ni, kita kena tunjuk 10 proof tu ke?
Tak. This one, it is a subset. So you just show it is a subspace. Okay. You just mention W is a subset of M2 by 2. Okay. So after this, there is one more, right? Number 3, KU is in W, right? After you show these 3, so you say W is a subspace of V. Ni kena ada, so it is a vector space. You only show using 10 axioms if you had to show for Rn, for Pn, for matrices in general, or the question said show the 10 axiom. Then you have to use the 10 axiom. Otherwise, if you are given just a subset of a bigger vector space that you know already, you just show it is a subspace. That's why only 3. Okay, next question.
Prof, nak tanya. Kalau A11 and A12 tu saya masukkan nombor salah.
Salah.
Okay.
If it is not, then you can put in numbers. If it is not. If it is, you put in number. Kalau markah ada 10, dapat mungkin maksimum 2. Tadi hari tu kan saya dah kata true for 1 or 2 cannot say true for all. So if you have to show in general, you have to show in general. You can never put in numbers unless it is not true. Jelas? Okay. You should be able to do number 1 until 48 ya. 48 sahaja. Other question? (31). Mana dia? Yang tanya ni cuba angkat tangan. Tengoklah juga mukanya. Hamiza. Mana? Tak ada, tak boleh on. Bukan nak tanya soalan. Dah awak yang tanya soalan, kan saya nak suruh jawab kan? Okay. 31. Assume S is x1, x2 is a linearly dependent set. Show for any x3 in V, T x1, x2, x3 is also linearly dependent. Okay. All right. So I mentioned this before. If a set of two vectors is linearly dependent, meaning it's a multiple of the other one, right? It is a multiple of the other one. What does it mean by linearly dependent? It means if you have this equal to 0, not all CI is 0. This is the definition, not linearly independent. So we can say C1 is not 0, or C2 is not 0, or C1 and both C2 not 0. Right? So if this is not 0, this is 0, phone saya tak pernah bunyi. First time. Sekejap. Bukan untuk saya. Okay, so we assume this ya. Kenapa call saya pula? Okay, so if this is not both 0, if anyone is 0, 0 is in the set, then linearly dependent. Okay, case 1. If C1 is 0 or C2 is 0, wait. Oh, no, sorry. I want both not 0. Mana boleh salah satu je. Vector ni memang tak 0 Alright. This is not 0, so C1x1 is negative C2x2. Because we can divide kan, kalau dia tak 0, we can divide. So x1 is negative C2 over C1 x2. This is the proof why I said that one is a multiple of the other one. Okay, now kita dapat ni kan. Next, if you add x3, you will get x1, x2, x3. Tambah So you want to get C1 plus C1x1 plus C2x2 plus C3x3 equals 0. Okay. This one, if I let C3 is 0. If I let C3 is 0, I only get this left, right? C1 x1 plus C2 x2 equals 0. Balik asal, it goes back to the original. Then you get this, which imply not all. C1 not 0, C2 not 0. So it's linearly dependent. Okay, meaning if it's already linearly dependent, you can add any more, it is still linearly dependent. This is like, okay, I have this and this, which is linearly dependent because this is 2 times this, right? If you multiply C1 1 1 1 plus C2 2 2 2 equals 0 0 0, you can get this is like negative 2 1. Can not all 0. If you have another one like apa-apa lah 1 2 3, it doesn't matter. You put 0 times that, you still get this. You still get the answer not 0. So this is the way to show it. You can skip this because it need proof. I already mentioned this in class. So this linearly dependent means not all 0 and it's a multiple. Then adding up one more, yang compulsory kena tulis, you have to write when this is 0, then you let C3 0. Ni dia punya key lah. You just let C3 is 0, then you go back to the original, and then you get to the not all 0. It's quite abstract. This is just to show you one example, but you cannot write your answer like this. You have to write your answer like this in general. This is a good question, yeah? Okay. It's the same for 32. Yeah, 32. If you have 3 linearly independent, now you cut 2, it will be linearly independent too. If you already have 3 linearly independent, then this one also linearly independent. Why? Because again, C3 is 0, right? So we have C1 x1 plus C2 x2 plus C3 x3 equals 0 imply C1 equals C2 equals C3 equals 0. Now you have only two. C1 x1 plus C2 x2 equals 0. What happened to C1 and C2? Only two. How can you write it? So since C3 is equal 0 for that, this is actually 0 times. So it's from the previous one with multiplying by 0. Then this also gives you, because C3 is also 0, so it's linearly independent also. You get this equal to 0 also. Any more?